So till previous video we have calculated that how to improve the gain of 5 transistor ODA. In that part I also taken the example of telescopic op amp, but here I will take few other structures also apart from 5 transistor OTA, and here we will calculate the common mode which need to be applied at the input and what are the output swings that we can get from a particular structure. So for swing and common mode calculations, we will see that how much input signal we can apply so that the transistors work in saturation. So everyone knows how to calculate this thing, but my point is not that. I'll take some different things also which may be asked in an interview. So this is my M naught. So first thing is that what is the common mode voltage? At input we will apply some DC voltage. So at input we will apply some common mode voltage that we call as VCM, and depending on this VCM voltage our all transistors are set in saturation. Okay, so what is the maximum and minimum value of this VCM can take so that complete structures work properly? Now first thing that for this particular structure we define this 2I naught value. This 2I naught, once this 2I naught value is given, with that particular value we can calculate the amount of VGS here, and so VB naught. The bias voltage VB naught is calculated from this 2I naught current. So I naught is flowing across M1 and I naught is flowing across M2. Now point is that if my 2I naught, which is already fixed by the design, what are the power specs and anything, so my B naught is it means what happened for particular I naught and particular specs, my M naught has some overdrive voltage. What the overdrive? M naught has the overdrive voltage that I can say OV0 or VD set 0. So this M naught cannot go below that value. So for finding the range of this input common mode that I am applying here to my structure, if we go on the lesser side, then what can be the minimum value of VCM? Because I know that for 2I naught, if VGS of M naught transistor is defined, then for I naught, VGS of 1, 2 is also fixed. For fixed I naught with VGS of 1 and 2 is also fixed. So if I am reducing my common mode, if common mode is reduced, if we are reducing the DC voltage that we have applied here, then what will happen? This VGS will anyway go to that, remain that value only, what is defined by current. So this VGS is anyway fixed. So this VGS is fixed, and what will change? Because I naught is flowing across this, I naught is flowing across this in DC condition. So this VGS is fixed. And if we are reducing this DC voltage on gate, then this voltage X, if I control this node X, then Vx will reduce. If VCM will reduce, means Vx is reducing, keeping VGS of 1, 2 constant. So what can be the minimum value of VCM? VCM min is equal to VGS 1, 2, which is fixed voltage, plus VD set of bottom transistor. If we go value of VCM less than VCM min, then what will happen? But our point is that the transistor should be in a saturation only. So this is the minimum value of common mode. Now what can be the maximum value? So if we increase the VCM, okay, if we increase the VCM, what will happen? if we increase the VCM, or means input voltage, DC input at both the input transistors, then we will see that by increasing this VD set not is already fixed due to the current. So what will happen, the Vx is enough greater than Vx is greater than VD set 0. So M naught is in saturation, not a problem. So higher the VCM, M naught will always be in saturation. So M naught is not creating the problem. Then who is creating the problem? One thing is that the Vx node is increasing, so M naught is not a problem. The problem will come at the input pair itself, because this VDS, we know this VGS is also fixed, because current in device is fixed, M3 current in M3 is fixed, I naught, and due to that current our VGS of M3 is defined. So what I can say, if I call this node as Y, then what will be the Vy? Vy is VDD minus VGS3. This is also fixed voltage because of fixed current I naught. Now where is the problem? So now I will tell one more concept. If my Vy is fixed and Vx is increasing, so we will come at the transistor M1 only. So for transistor M1, this is my M1. What is happening? This is my Vy and this is my Vx. This is increasing and this is fixed, and this we are increasing. So what will happen at one point in time? What will happen? This node can go maximum at the value of 1 VT up. This is Vy, not a problem. So this is 1 VT of this transistor 1, and this is my VCM max that I am increasing, and this is my Vx at that value. So this concept is that VCM maximum can be equal to Vy plus VTH1. And what is Vy? It is my VDD minus VGS3 plus VTH1. So this amount was already constant, this is now constant. So VCM max is defined. I'll take this concept for both the transistor right away. So in between I should tell my VGS calculation. I think all of you know, but if someone is not known to that, I'll write here for this VGS also. For any transistor, whether it is NMOS or PMOS, if I am pumping a current, or if a current I is flowing, or I will say ID is flowing, if in transistor in saturation, then what will happen? A VGS will be generated, and this VGS will be what? From the current equation itself, 2IDY mu n COX WIL plus VTH. So from here we can see VGS is defined as this value. So VGS minus VTH, which we also call V overdrive, also called VD set, equal to this amount. Okay, so for fixed current, this VGS across any transistor is fixed. So now I will take that concept which I am telling, that at what is the edge of saturation we can directly see. It will be very helpful when we will be calculating the swing in bigger structures, or we will calculating the any node voltage maximum or minimum in the big structure. Then it will be helpful. So this concept I will take. I will say tip. Okay. So what is this concept? For NMOS, this is VG, this is VD, this is VS. So when your VG is just 1 VT up of VD in case of NMOS, then it is saturation edge, or I can say edge of linear as well. And when this case is like that, when this potential is slightly greater, or anyway it is greater than VTH, then you can say your transistor is forced in linear. And when this is greater than, when this gap is greater than, sorry, less than VTH, your transistor is in saturation. So the minimum condition in case of NMOS, we always say that our VG can maximum, or VG and gate voltage can maximum go 1 VT up of drain voltage. If it is going more than that, then your transistor will be forced into linear, and that is not a desired reason for amplifier. So this concept we will use thoroughly when we will calculating any swing for any structure. I will take few structures also. So for PMOS, this is for NMOS. For PMOS, this is my source voltage. When this amount is exactly equal to VTH, I am taking a magnitude here because it is PMOS. So it is edge of saturation. Same concept apply here. Be aware of this thing, that here I am taking the magnitude of VTH, and VD can go maximum VTH magnitude up of VGS. In this case, this is also forced into linear. This gap cannot go more than VTH magnitude I am concerned about. So don't be confused while using it. Deep into the saturation or saturation. Okay. So this is for PMOS. So this thing we will use in the structure because the 5-pack structure is simple, so we can easily calculate the input common mode swing. So what input common mode came for 5-pack? Okay, so for OTA, 5 transistor OTA, what is the swing came for this input pair? So this is the maximum and minimum value of our common mode that you can see from here. So these are the minimum and maximum value. Now if I want to calculate the output swing, the minimum value of, first I will go for the maximum. Max value will be what? VDD minus VD set of 4. 3 or 4 means same. This is transistor 4, this is transistor 3. Yeah. So what is the minimum value? For any particular value of common mode, again apply the concept of the same thing, that for the NMOS, for M2 we can apply the same concept. Then output minimum value can be what? It will be VCM minus VTH of 2 or 1 anyway. So it is not, magnitude is not required because it is a NMOS. Okay, so this is the minimum value. Any VCM can be here because we calculated this is the range of VCM. It is not an exact value, it is a range. So if I am biasing my transistor in some between value, if this value, let's suppose this value is my 0.5 milli and let this value is my 1.5 milli, so I will somewhere on the millivolt, so I will somewhere bias my this pair at 1 volt. So we will apply here this 1 volt, 1 minus this VTS2. Okay, so whatever the present common mode applied at the input, we will use that particular value of common mode while calculating the minimum value of output. So this is the output swing. Now I will go for the telescopic structure, where we will see that the swing calculation is a bit tricky, and if we miss some things then it may be incorrect. Okay, so these are the cascode device, this is my current mirror structure. Okay, so here we will see that this is my output, this is the input. So input I am applying the common mode both the side or I will short it here. This is the common mode applied and VV naught. I told you that if we are setting to I naught, according to that we will set the VV naught, so not a problem. And this voltage, so for this structure when we will calculate the swing and common mode, this voltage I call it BV34 is defined from some external source. I am not caring about it. This is a biasing circuit. We will set the BV34. So what is the point now? These two voltages are already decided by the current, because these are the diode connected devices. So current flowing in DC condition here is I naught, and according to I naught VGS are set. So this VGS of 3 and VGS of 7 and VGS of 5 are deciding these values. So this value, if I call this node Y, this Y is defined, this Z is defined, and what do you say, this X node is defined, and this called VV34, this is defined by external biasing circuit. So what can be the minimum value of common mode? I will directly go ahead here. What is the minimum value? Minimum value is again nothing but a VGS, which is fixed value defined by the current, VGS of 1 2 plus VD set of transistor M0. So this is the minimum value. It is same in both the cases. So now for the maximum, what you will see here, in case of maximum value, we have to concern about this node. Let's tell this node W. So what is the value of W? So VW is nothing but VB3, 4, which is the external voltage, minus VTH of 3. So this is the VW. So what can be the maximum value of common mode? From the same concept that I given in the tip, this VCM can be maximum as W plus VTH of 1. So it is nothing but BB 3, 4 minus VTH 3 plus VTH 1. Now point is that from where this VB 3 and 4 is coming. So I will tell also about its the minimum value. Okay. So let's see it here only. So what is VB 3 and 4? So first we will see that what is the minimum value of 3. So for defining the minimum value of VB34, because I naught is fixed, so it will be nothing but VD set of 0 plus VD set of 2 plus VGS of 4. So this is the minimum value of this node VB3, 4. So if my BB is some voltage, VB3, 4 is some value which is used here to bias this node, which is greater than this value. So I don't know what is the value according to these specs. We will have some this node value VB3, 4, and it is nothing but a greater than its minimum value, and we will use this value here in the expression, and so that we can find the maximum value of common mode. So this is the maximum and minimum value of common mode. Now if we go to the swing calculation, output swing calculation, then what is the maximum value of output that we can see? So maximum value of output is directly defined by VDD minus overdrive of device 8 minus overdrive of device 6. Okay. So from here we can see that the output can go the maximum value. Now if we consider about the minimum value of output, then again I will say apply the same concept that I told you in tip. It will be nothing but VB3, 4 minus VTH of 4, and this value I know, and whatever the value we defined here, it is greater than this value, and from here we can calculate the output minimum and maximum value. So from here we will calculate the output swings, and from this section we will calculate the input swings, that we can apply the maximum. So this is the one structure, but here is a swing limitation problem. I am not telling about this thing, but yeah, it is important for the interview. This particular structure that I am using as a load, that the PMOS diode connected devices, two back-to-back diode connected devices are consuming more headroom. So this problem I will discuss in some time. So before that, I'll take one more structure and calculate the swings. Telescopic amplifier with wide swing current mirror. Here my concern is not telescopic structure or anything, but yes, the point is that swing calculation is very important, and they can give you any arbitrary structure, random structure, and you have to calculate it. So two things we have to always keep in mind, that for any particular structure, one thing is defined, which is my current, and if current is defined, then we cannot do much about the BGS. Okay, so this is my wide swing current mirror is used here. So again, I will numbering the device 1, 2, 3, 4, 5, 6, 7 and 8. Okay, so here point is that I have two nodes which are not biased yet. So we'll proceed in our one thing we know, current is fixed, so VGS of all the transistors is fixed. But point is that are all node defined or not? This is my VCM. So Vx is defined, VCM is already I have written. So this node BB34 and this node BB56. So these are not defined by the structure or the current inside this structure. They are biased externally, but this node is defined. So if I give the numbering, this node I can say some Z, so it is defined. This is X. Okay, this node I will say as Y for time being. So now I have to think how to calculate the minimum and maximum value. So I think there is no problem in calculating the minimum value of common mode. So the minimum value of common mode is again coming what? VGS of 1, which is defined by the current 1 or 2, it's same, plus VD set of transistor M0. Yeah, this is the minimum value. Now I'll go for the maximum value. Now I'll say that concept is already explained, so you see it. So it is nothing but Vy plus Vth of 1. Vy, we know that it is nothing but VB34 minus VGS of 3 plus VTH1. So this is the maximum value of common mode, and VB34 is coming from where? We can see that the minimum value of it is already defined. VB34 min is already defined. Its min is nothing but BD set 0 plus overdrive value of 2 plus VGS of 4, which is defined by the current. So this value is defined. Again, at the same time, if I go for before going to the output swing, I'll also write the maximum value that my this 5-6 node can take. For this lower node, that is a 3-4 node, the minimum value is defined, and for this the maximum value is defined. So in practice, these nodes are biased at a value, the VB3 greater than a VB3 minimum and VB56 less than the max value. And what is the max value? It is a VDD minus overdrive of transistor 8 plus overdrive of transistor 6, so overall minus, sorry, not 6, here mistake. So it, instead of this I will write VGS 6. Okay, so the maximum value of M6 is defined, or sorry, V56 is defined. So from these two equations we can see that our BB 3,4 is some value greater than the minimum value. Okay, BB, so it is something which is greater than minimum value, and BB56 is some value which is less than its maximum value. So we are not worried how to define this value. These values are defined such that this. Okay, so now if I calculate the output swing, what we will see that output max, Now we will not go to that VDD minus overdrive of 8 minus overdrive of 6. We will see that my VB56 is already defined. So from that I will apply the concept of tip that I explained for the PMOS, which is that the maximum value can go VB56 plus VDT of H of 6. This is the maximum value my output can go, because my VB56 is already defined from here. And what is the minimum value? It is BV 3,4 minus VTH 4, and 3,4 is already defined here. Okay, so we can see here the output's maximum and minimum value. And if we compare these two things, I'll say this is the not only the value maximum that output is getting. One more value that output can get the maximum is that, I'll change my color. Okay, let's say green. Yeah. So one more thing that person can think is that V max can be VDD minus VOB8 minus VOB6. I have written the OB, and this is also overdrive. So anyway, VOB equal to VD set, same thing. Okay, so this can be the minimum value, sorry, maximum value, and minimum value can be also V overdrive of 0 plus V overdrive of 2 plus V overdrive of 4. So what we have to see, we can calculate the output maximum and minimum value individually. Then later we will see what the output will be, what the maximum value of output will be, means a minimum of these two, and minimum value of output will be maximum of these two values, red and green. So from there we can see what is the exact output swing we are getting. So this value we have to define. This is my minimum value and this is my maximum value. So maximum value is nothing but the value minimum of these two values, one value and two value. So and minimum value of the output will be maximum of these two values. So from here we can calculate properly. Okay, so the swing can be calculated properly, no need to worry. So these are the two examples telescopic are taken just to calculate this swing and understand the concept of common mode range. So I think this is enough for this video. Later I will explain one more concept that I left behind. What was okay, while explaining this swing, okay, yeah, this concept of why I choose this, why I choose wide swing current mirror. So the question for the homework is that limitations, spelling is incorrect. Okay, limitations, yeah, limitations and advantages. So for I am just drawing, you can see it. From here you can analyze and what is the problem in this structure over this wide swing structure. Okay, so what is the problem? This is my input current, and also I want to see here itself. I will give one more question, that I want to see input resistance in both the cases. Okay, so this is enough for this video. This is the homework, you should solve it. I'll explain about it in the next video. Okay, later we will come back on again on 5 transistor OTA. So this is enough for this video. Thank you.